Hey everyone, it's a real pleasure to be here at ICFP. My name is Patrick Thomson.
And I'm apparently Rob Ricks.
And we're here from GitHub. Show of hands, quick, how many people use GitHub regularly? Oh, wow. How many people kind of sometimes use GitHub for even maybe once or twice? Excellent. Not a lot of SourceForge users in here. I'm glad that we're in a safe space.
Okay, so Patrick and I have known each other forever. Sorry, I guess I should actually be using the microphone. Apologies for that. Patrick and I have known each other forever. We've been working together for several years as well. We've been fans of typed functional and programming as long as I can recall. Patrick is the one who taught me applicative. And fans of ICFP in particular as well for quite a long time. So we personally are quite strongly motivated to be speaking to this audience. But additionally, from GitHub's perspective, well, there is a lot of code on GitHub. The fact that almost everybody here uses GitHub is probably an indicator of why that might be. Given that fact, it'd be nice if we knew anything about it. So who are you going to ask but folks who know something about programming languages?
So one of the tools that we've built to try and understand and comprehend the corpus of code on GitHub is called Semantic. It's written in Haskell, and it supports 9 separate programming languages. We'll get into those later. And we built it to prototype and to power real, actual, honest-to-goodness GitHub products that actual people use.
Products like, for example, the table of contents. Now, sadly, you can't actually find this one in the app anymore. If you're familiar with pull requests on GitHub, however, in the pull request or PR view, there used to be a way to go and find a little drop-down that would show you a table of contents of what had changed in the file. Now, you'll notice some of the entries here are in green, some are in yellow. Well, we have inserted, deleted, changed in yellow files and symbols within those files to help you navigate your way around what might be quite a large pull request code review process. This was, again, computed almost entirely with the guts of Semantic.
And another product, and perhaps our main, the Semantic code team's main product offering, is code navigation. Originally, this was prototyped in the Ruby on Rails monolith that powers GitHub.com via shelling out to the venerable ctags executable. It may not shock you to learn that that approach doesn't really work at the scale that GitHub is at. So we took Semantic and hooked it up to an RPC framework, servant with all of its fancy types, and we allowed people to navigate code, jump to definition, and find all references on GitHub in the 9 different supported programming languages. Now, at this point, this code doesn't the code navigation service is built on a DSL. This is not reflective necessarily of Haskell being the wrong tool for the job or Semantic underperforming. Semantic did a killer job in practice, but what we want is community involvement. The Semantic code team is a small team. We've been 7 people at max, and sometimes even only 4 people. And we want language communities to maintain their own rules and heuristics for code navigation. So we've implemented this as a DSL, and we just passed the DSL off to the Elixir programming language community, who implemented and now maintain their own code navigation rules on GitHub. We think that's pretty cool.
So again, small team, big problem. Lot of languages we want to support, and supporting stuff across languages, trying to find any commonality between them is kind of an interesting challenge in and of itself. Functional programming is concerned with solving large problems by breaking them down into smaller problems, and this is what we were hoping to do. And so with that in mind, let's take a look at 4 case studies of how that played out.
Before you do anything with any program text, you need to parse it. And the unpleasant truth is that in a lot of corners, people consider parsing a solved problem. And in real world, there's just myriad approaches to parsing. Ruby uses a Bison parser. Python uses their own homegrown parsing expression grammar framework, and most of the GCC projects parsers are actually handwritten. I hope you enjoy maintaining a handwritten C++ parser. That job must fall on somebody. I wish them the best of luck. In an ideal world, we'd be able to use the native tooling for every language. Obviously, there's nothing understands a language better than the tools that underpin it and were written by its authors. But that's just too operationally complex to fly in an environment like GitHub. We can't maintain n language stacks for n languages. We need some sort of coherent interface that allows us to parse a whole variety of different languages in sufficient time, in sufficient space at GitHub scale.
One of the ways that we built on, oh, actually, I guess that comes later. Yeah, so TreeSitter was developed by one of our teammates, Max Brunsfeld, initially for integration into the Atom code editor. It has since been integrated successfully into Atom, but also into VS Code, into NeoVim. I think Patrick mentioned Emacs today, maybe yesterday. Emacs. That's pretty cool. It's kind of cool. It lets you write a grammar in a DSL in JavaScript that ends up looking a lot like parser combinators, so quite familiar to myself and many others in the functional programming community. And perhaps most importantly, it gives us a consistent API that we can use regardless of what language we are actually parsing. So the grammar is taken, then compiled down to a C file. We compile and link against that, and then talk to that through the Haskell FFI.
Now, TreeSitter is based on the generalized left-to-right algorithm developed by Lang in '74, and which, interestingly enough, took a decade plus to be actually implemented in practice. This algorithm came out of the natural language parsing world. Natural languages, as we all know, are riddled with ambiguity and complexity and possibly even non-deterministic interpretations. And these techniques were developed to have a framework and an algorithm that's capable of understanding even the most Byzantine and complex grammars. And speaking of Byzantine and complex grammars, Ruby is sort of our measuring stick for whether something is capable of handling real-world languages. Ruby, though on the surface may seem a very beautiful syntactic language, is fiendishly complicated. But we're happy to report that that TreeSitter, combined with a custom lexer, that's a fairly small C program, is capable of handling all of the 9 languages that we've chosen to parse, and that the generated C code is fast enough to be integrated into a high-performance service, servicing the entirety of GitHub's user base.
As a quick side note, Ruby is also the most complex in every other way in addition to syntax.
That's true. That language has all of the things.
It's the source of many joys and many pains. Anyway, so as a second case, I mentioned earlier that the complexity of trying to do all the various things we're doing across 9 different languages led us to want to consider, well, how can we factor that work out? We'd like to, for example, treat the pretty printing, for one example, of integer literals the same way, regardless of whether it's in Ruby or JavaScript or Go or etc. That isn't necessarily going to give you a source level printing, but it's a way to share some of that structure, some of that work, trying to reduce ultimately M features across by N languages up from this huge M by N polynomial down to simple M plus N line. That's what we want to be looking at. So one attempt at this was to factor out bits of syntax like integer literals into individual data types that we then combine into an a la carte style sum type. Now here we've got an array sum instead of a binary sum, but the principle is the same, that we take a union of all of these different shapes of syntax, gives us injection into it, and crucially, safe projection back out. And it's compatible with working with recursion schemes. You could throw fix or free around this and have something that you know how to fold over.
It's also worth mentioning here that we'll see in this little language that we've included a parse error case, and that's crucial because at GitHub we can't assume that all the code in a repository is well formed. Maybe somebody made a syntax error somewhere, or maybe they've introduced new language syntax and we haven't integrated it properly into our parser yet. Tree Sitter, one of its many virtues is it's capable of doing a best effort parse of a possibly malformed syntax tree. So throughout, we were able to reify that property and make it visible in our syntax trees. Data types a la carte is a fantastic classic paper, and I can't recommend reading it highly enough if any of you haven't yet, but it has a problem in that the standard encoding of an a la carte of the injection and subsumption relation is expressed with recursive overlapping type classes. And while this works for your smaller languages with maybe 20 or 30 different syntax types, a language as complex as TypeScript has over, and I'm not kidding, 140 different distinct syntax nodes. And when you feed a GHC, a type level list containing 140 different items, GHC tends to become unhappy. So the solution was to do some loop unrolling in the type system, which sounds madness-inducing, but is actually a bit of a throwback back to the 70s with C programmers and Duff's device. And by unrolling, oh yeah, I heard some knowing laughs there. When that's unrolled with some template Haskell that would make your eyes bleed if you ever looked at it, it worked fast enough. And so we took this approach and published it as a library on a package called FastSum. And it's open source, it's out there, people are using it, we're using it.
So the way this all started, in fact, the reason that I work for GitHub, period, was because I used to work on a diff tool called Kaleidoscope. Well, now I work at GitHub. I was interested in how can we do diffing differently. I mean, diffing is kind of core to GitHub's product. One of the key things that GitHub offers, if you're not familiar with the product, I should have mentioned earlier, GitHub is source code hosting and code collaboration for communities of users of arbitrary size, from small teams up to quite large companies, or external to companies' teams, communities rather. And the one of the key atoms of the UI is changes to code. You've made some change, you're suggesting that I adopt that change in my project. Well, I want to be able to look through, review that. I want to have some discussion with you about what it's for, why you made this choice, ask you to change something perhaps, so on and so forth, and hopefully make an improvement to it that everyone then gets to benefit from. However, diffs are limited. Mostly we look at textual diffs. If we're looking at textual diffs, that's fine if we're dealing with lines of text, but usually we're not. Usually the structure of what we are trying to compare is much richer than that, and we're leaving most of that structure on the floor if lines are all we consider. To that end, we developed algorithms for doing syntax-aware diffing. These were then refined somewhat in conversation with actually some folks in this community, Wouter Swistra and Victor Meraldo in particular. And some of the resulting comparisons we got were kind of cool, because if you move something in a textual diff, you're deleting some lines, you're inserting some lines, but there's no notional comparison or relationship between the two. Or for example, if you're doing the thing where you insert a function with curly braces, one of those languages uses those, and it's shown it as the first line within the braces down to the last line inserted. I forget the right structure of this, but it basically gets the braces in the wrong spot simply because the algorithm happened to end on a 1 or a 0 rather than a 0 or a 1. It's a frustrating way to look at your program or to try to understand its changes. So we developed this. It works really quite well as far as we're concerned. But we found it difficult trying to build good products on top of this. Our first attempt was a notion of summary, which was to try to compute a human-readable summary of what changed within a given diff. This turns out to be terrible if you do it the naive way that we approached it, because what ends up happening is you say, deleted 3, inserted 2 or replace 3 with 2. This is not going to be an improvement on just looking at, -3 plus 2 in the diff. So that particular product feature didn't sail, but as a whole capability, we're pretty happy with structural diffing.
And what fell out of our first approaches to diffing was really gratifying, which is the utility of recursion schemes in a real-world context. Diffing is the process of comparing chunk by chunk syntax trees, and that is a recursive operation over syntax trees. And it turns out in practice, most of the things that you want to do with a syntax tree can be expressed as a recursion scheme, whether it's a fold, it's usually a fold, that's the universal destructor, but unfolds are very useful as well. They've turned out to be a magnificently useful tool in our toolbox as programmers. They're compatible with our a la carte approach. You can see on the right here is a very simple recursion scheme over the small term language we showed earlier, and we see the application of the katamorphism there. And the kata, aka the standard fold, is fairly innocuous. Even the more exotic recursion schemes like histomorphisms came in handy when we're doing. Did we do zygomorphisms or feudomorphisms?
I believe the prepromorphisms.
The prepromorphism. That's what we did.
An appearance. Finally, our perhaps most exciting to me personally application of what we're trying to do here is just program analysis. As I said before, we have all of the source code in the universe. It would be really cool to know anything about it. If we leave it as just blobs in Git storage, as just text on diff, that's a real waste. That's a waste of potential knowledge. So therefore, we looked to the literature again for ways that we could try to analyze and understand, answer questions about our programs, our users' programs. Abstract interpretation was a natural starting place just because it is so general and so powerful. But in fact, it's those same properties that kept us there. It's not just that, oh, it's general and isn't that nice, we could have applied to anything. It's that actually this is really open-ended for us. This is a really interesting question of research. We don't know what questions are important to ask. We don't have a way to gauge what questions are going to be important to ask next week. So if we bake ourselves into something that's a little too tightly focused on one particular kind of analysis, that's going to be a shame. We're going to regret that. So we built on abstracting definitional interpreters. If you haven't read this paper, by the way, it is one of my all-time favorites and always will be. And this is the on an ongoing basis, this is the primary focus of development on Semantic. It's also my personal, again, my personal joy, but also my personal focus in my work wherever possible. It did pose some interesting problems though. Like for example, it wasn't exactly obvious how to take the approach as described, as implemented in the paper, and implement that in Haskell with the tools we have commonly available to us, like, for example, the MTL.
Indeed, the paper in the Abstract and Definitional Interpreters paper, its artifacts are implemented in a monadic style, but not in Haskell. They're implemented in Racket, atop some Racket macros. To overcome the problems that a traditional MTL-focused view of the world the problems that a traditional MTL view of the world encounters when implementing ADI, we turned again to the literature, mostly the papers of our co-authors, Nick and Tom. And Rob went into the shed and with a great deal of clanging and bashing, emerged 2 weeks later, slightly bloodied, but with an effect system, a practical, real-world effect system that is performant enough for the GitHub use case that allows having multiple state types or multiple reader types in the same computation, which is not possible with the standard MTL approach, and that allows one of those state types to have a differing interpretation from the other, which is really crucial when non-determinism enters the picture and you want one state to have all possible paths changes reflected in it, and in another state you want only the winning path to have those changes propagated. That is also published as open source software. There are people out there building their businesses and websites with FuseFX, which is humbling and honoring. It's got like more than 10,000 downloads, I think, at this point on GitHub, so that's pretty cool. We're really happy with it.
On Hackage. On Hackage.
Oh, goodness, yes.
Yeah, and as a quick extra note about FuseFX, it's also an ICFP story in that it was started, its first commits occurred on the steps of the building outside. I can't remember which building it was in St. Louis, but from ICFP in what was that, 2018? Something
2018,
like that.
Yeah.
So, and it was immediately post a conversation with Nick Wu. So thank you, Nick. So in conclusion, we've done some things, and some of those things were hard for some reasons. And because of those reasons, we applied some other things. But the things that we applied would not have been available to us without the work of ICFP, and like the ICFP community, the functional programming community, the academic community, and the research-oriented industry programming community as well. So I just personally would like to say that I'm just incredibly grateful to everybody for your work.
Thank you. Rock. However, I'm in the grand tradition of people with mixed news. I'm going to break the bad news first. We know some of our techniques just worked beautifully the first time, but some of them encountered a little bit of some ups and downs. The traditional encoding of a la carte syntax that we showed earlier is very cool, very fluent to express in Haskell, but has one large drawback in that you must give up a little bit of type safety because the subterms of when we express syntax with functors, the subterms are of the type variable associated with that functor. So in the standard approach, you're not able to say, all right, in this particular term, we know that such and such is going to be only one of these three types. It could be really just about anything. Now, there are approaches, Patrick's approach with the comp data library that work around this, but you do pay a pretty heavy cost in terms of complexity. And what we actually realized was that our hypothesis that we would get good code reuse by handwriting and reusing these data types, the degree of code reuse we got there was less than the code reuse that we did when we started generating Haskell syntax types directly from the grammar descriptions. And this was a really interesting result in that it suggests to me that the higher level things that you can reuse, even if they lead to perhaps a proliferation, or if that's a word, of data types, that gets you more compelling code reuse. As with large Haskell projects, build times do become a problem. We've used the Bazel build system to work around those. Editor tooling, nowadays the Haskell language server is in a really terrific place, but back in 2018 it was a bit shakier, especially with large template Haskell splices that we have. Something we do run into is that generic programming in Haskell can be very difficult. With the standard GHC generics library, the programmer needs to have a familiarity with type families, with polykinded types, and taking a novice Haskell programmer and sitting them down in front of that interface is a little bit difficult. We also had a brief experiment with typed file paths to catch any errors we might be making when we tried to append a file to a file path to a file path, and whereas allowing the appending a file path to a directory. This did point out some places where we were having, shall we say, creative semantics for what was being passed in, but it didn't really catch any critical bugs, and it posed a good deal of computational complexity and reading complexity atop that.
By contrast, at one point in time, every push to GitHub of any code where at least one of the files was in one of the 9 languages we mentioned, or showed anyway, went through Haskell code. That's pretty damn cool. That seems to me to be a pretty tremendous win. That we're talking about a lot of runs, a lot of instantiations of the process. So pretty fantastic. Tree Sitter likewise became foundational, not just for us, but for anybody doing parsing for developer productivity in any way, shape, or form. It's really been tremendous to see Tree Sitter take off. The community that's grown around it has just blossomed. Likewise, recursion schemes. Folds, who doesn't love a fold? Come on, folds are great. And it doesn't matter if you call them folds or catamorphisms, they're still folds. They're still beautiful. Algebraic effects, likewise, I will never not love algebraic effects as well. It's just tremendous to be able to decompose programs into DSLs like this. And it's pretty neat also that we were able to find several places in which we could decompose part of our system into an open source package that other people could use, and sometimes even did.
It's fantastic. There was a brief anecdote that I wanted to tell about our scaling requirements and operability, that our deployment of Semantic in production never actually hit any crashes or errors, except for one, when something deep inside the GHC event loop croaked and died. And we submitted this on the GHC bug tracker and got a reply back in a couple of hours saying, "Are you running Dell servers?" I'm like, "There's no way." And so I get on the horn and I find out what brand of servers. And yes, they were Dell servers. And yes, there was some configuration of the BIOS that made Linux's epoll fall down in a given critical situation. It's horrifying, it's terrible, but most of all, it's not our fault. And that's just terrific.
Thank you very much.
Yeah, there's that.